Good morning and welcome back to the MCAT grind. We have Organic Chemistry Chapter 7, Aldehyde Ketone Part 2. In the last chapter, we talked about aldehyde and ketone and their structure mostly. And to differentiate them, remember aldehyde has H in it, so it has a hydrogen attached to one of the sides, and ketone has both sides of the carbonyl carbon attached to carbons. Now, we have talking about more of an intra-compound reaction now, including aldol condensation, probably one of the more prominent ones that will come up, and also the basic of keto-eno shifts. So in its base form, we have the keto form of the aldehyde or the ketone. What that means is the carbonyl carbon is attached to the oxygen in a carbonyl form, right? Double bond. Whereas if you shift to an eno version, because the oxygen can take away one of the electron bonds, and to do that and bind to hydrogen, and then shifting the double bond to the carbonyl carbon and the alpha carbon over here. The alpha carbon is one carbon away from the carbonyl carbon. So this is alpha carbon, this is also alpha carbon. A beta carbon is when it's two away. So this is alpha and that's beta carbon. Okay, just a heads up. Next, what this does is that in any solution equilibrium, if condition allows, they will do this keto-eno shift, but the keto form has a much better stability, so it will favor keto form much more than eno form. However, in a basic solution, the electrons will be forcibly pulled off, and that will allow what we call an aldol condensation, where this carbanion, where it's negatively charged now, if you pull that H off, it will shift to an eno form, and then this new carbon will then attack another compound, and when it attack at the beta side, remember alpha is one away, beta is two away, the beta carbon, it will cause a conformational change. This 2 will be jumped, this double bond here will jump to here. Alright, and it will shift this bond up and back down, so it will form a new bond like so. What that means is you can not only do this to another random molecule that has a double bond on it, causing the shift. Remember, this will act as a nucleophile attacking a nucleus, and this is an electrophile attracting the electron. You could do this within its own solution. Then we have the aldol condensation, which means that the aldol, after making the eno form, the eno here, the carbon, eno carbon will then, alpha carbon will then attack the central point of the carbonyl carbon, and then it will form a new bond here and push the carbonyl carbons double bond into the O, and that O will then go ahead and grab another hydrogen molecule and turn into OH. This H is not denoted in this, but now the central carbonyl carbon is no longer a sp2 shape. It's now sp3 because 1, 2, 3, 4. It has 4 bonds. Here it's bonded to H, but you can't see it. And what this means is that there's an aldehyde right here. There's a carbonyl and an H to the side, the other side is a carbon, and we also have an alcohol on this side. So that's why it's called an aldol. We can reverse the aldol reaction by adding loss of base and loss of heat, filled with water, so it will cause a hydrated base, and split the aldol into the aldehyde and alcohol, which generally just go back to the aldehyde because the alcohol will lose the H to the base and then turn back into a carbonyl. So using strong base and high temperature, we can achieve the aldol condensation state. That's the only way to really get the reaction going. Otherwise, it will really just stay as a keto-eno shift form. We can also apply this to imine and enamine, which imine is just the same thing but carbon bonded to N instead of to O. And an enamine is the eno equivalent, where it's shifted from the carbonyl imine to the N to the alpha carbon. Hopefully that's cool.